Alright class, let's continue. So now we know we need to use convolution integral to calculate a zero state response. But how do we do the calculation, right? You have basically solve the integral in the general case. But this is a signals and systems class, and I don't want to constrain you on some basic calculus techniques. So we're going to discuss some special cases. In a special case, we'll need you to utilize what is called the convolution table. The convolution table is table 2.1 on page 125 of our textbook. It lists a number of pairs of f1, f2 that we'll put into the convolution integral, and we'll give you the result. We're going to use the convolution table in this class whenever I ask you to calculate a convolution integral. So make sure you can use the table properly. You in class examples, in your homework, in the exam as well. So that being said, let's look at an example. I'll illustrate how we can use it directly. So let's say I have an LTI system, and this LTI system has h of t given to negative 3t u of t. And I want to know that, or I want to be able to find the system's zero state response for f of t equal to 1 plus e to the negative t u of t. Alright? So for this example, of course we can use the results directly, but let's first make some observations. Observation number 1. Is, well, h of t has some special terms, right? The first thing you can see is everything has to be multiplied by u of t. Or in other words, h of t is, for this example, h of t is 0 for all t less than 0. For this example at least, right? What does it mean? It means the unit impulse response appear only after t equal to 0. After that. And t equal to 0 is where the input signal is applied. The input to h of t is delta t, the spike at t equal to 0. So this observation tells us what? Tells us the system is a causal system. The system is a causal system. Alright? That's the first observation we made. The second observation is, if we generalize this discussion by plugging that into this equation. Since we already find out h of t will be 0 for all t, or the argument negative, and the argument is like this, right? It means this argument is less than 0 when tau is greater than t. And this is the range where you will have a 0 in your integral. Its term will be 0 in this range. And since tau is the integral variable, it goes from negative infinity to plus infinity. And since you don't really want it to go beyond t, since beyond t you know the integral in that part will be 0, you can further write it as negative infinity to t f tau h of t minus tau d tau. And this is because the system is causal. And as you can see, what it said is, if you look at this terms, now f of t, or f of tau, doesn't go beyond t, or in other words, your output at time t only depends on your input before this particular time instant. That is what causal actually means. That's your first observation. When you see this u of t in your h, that indicate that your system is causal. Second observation. You have two exponential signals. What does it mean? It means two things. It means these the characteristic modes of the system. Second, that means you also have the characteristic roots. Okay? Or in other words, from your unit impulse response, you should be able to find the characteristic modes and the characteristic roots by extracting the exponential components. Okay? And you have to pick all the terms. If there's a 1, that means it's 1 is e to the 0t, right? So 0 will be one of the characteristic modes. Okay? So these two observations are sort of important, especially the second one. You can use it to extract some of the most important information from a given system. Now let's go into the calculation. The calculation is y of t, zero state response, is f of t convolution integral with h of t. F of t is 1 plus e negative t ut. That's what I have up there. Convolution integral with minus e to the negative 3t u of t. And keep in mind that multiplication and convolution integral are two different things. Do not mess up with them. They shouldn't be confused with each other. Moving forward, expand them into two terms. The first one, negative t ut. E negative 2t ut minus e to the negative 3t ut. Need to apply property number 3 appropriately. Try to distribute the terms. When you do that, you will find out that you have two terms in the first pair of brackets, the set, and two terms after that. And altogether, when you distribute the terms, you should have exactly 4 terms. And the 4 2t ut minus ut convolution integral with e to the negative 3t ut. And keep in mind that you know what is multiplication when you're doing multiplication. The convolution integral, and then plus negative 2 ut. This is one signal. It will convolution integral with this a little bit. So complete the last term. So e to the negative 2 ut, convolution over e to the negative 3t u of t. And for each pair of them, you will be able to find out a pair in the convolution table. So the convolution table reads like this. I'll write the first it says if it's e to the lambda t ut, the other is u of t, the convolution integral will be 1 minus e to the lambda t. There's no parentheses either. U of t and e to the lambda 2t u of t. If lambda 1 lambda 2 are not equal to each other, the result will be e to the lambda 1t minus e to the lambda 2t divided by lambda. This is what you will find in the convolution table. And when you plug this into the equation above, you will find out that y of t is equal to, for instance, plug in the first term, and the ut there, so will be 1 minus e to the lambda 2t over minus negative 2 will be 2, so lambda will be negative 2 here. Times u of t. Then plus, right? Now you have lambda 1t, lambda 2t being the two lambdas. So minus 1 minus negative 2, e negative t. Negative 1, negative 3. So what do you have? You have negative t minus negative 3t again. Minus 1 minus negative 3 ut. And lastly, you can organize the term appropriately to find the result. Okay? I won't go into that. That will be just some natural steps. Okay. So this is the example. Now, the final result of this, which I will give directly without giving the organization steps, is this. And it's easy to find. Well, if you look at the terms, right, you have sort of constants multiplied by u. You have negative 2t, negative 3t, and negative t. Really nothing else. So when you finish this, you'll find out that this will be equal to 1/6 plus half of e to the negative t minus 3 over 2 e to the negative 2t plus 5 over 6 e to the negative 3t. And don't forget about u of t. This will be the result, right? Now, again, we should make observation again. And I just sort of brushes through this already, that you have 1, you have negative t, you have negative 2t, negative 3t. And also we made observation earlier that e to the negative 2t, e to the negative 3t are the characteristic modes. Well, for the input, we have this constant and e to the negative t. And the constant is not a constant, it's just 1 times u of t. So you can view this as e to the 0t. Now, all 4 of them appear here. And naturally, because the way that we discuss them, it's possible to say or divide these into two groups. This is sort of the input induced, and the second group is sort of system induced. Because the system itself has e to the negative 2t, negative 2t, negative 3t. Well, the constant term and the e to the negative t come from the input. Okay. And this gives us another way to characterize or classify the terms. And sometimes we'll call the input induced terms forced response, and the system induced terms as natural response. Okay. And this is just based on which modes come to this, which term comes from the system, and which term comes from your input. Slightly different from what we discussed earlier, how we decompose the total response into zero input and zero state. Okay. Now, since to think about, I'll raise the question and I'll give you the approach to solve this, but I won't give the solution. You'll find the solution yourself. What if I'll give two questions? Your f of, I solve for one term, but let's assume I have this. The input is modified to the following. What if the input is changed to this? Okay, if you compare f of t here to what we have above, you should see a time shift in the input. Since for every t in this equation, I replace t with t minus 3. So I delay the input by 3 time units. Question is, what will be the response? Okay. Second, what if my input is like this? Okay. Can you find a solution to both of these questions by reusing what we have solved above and applying the property or the assumption that the system is linear and time invariant? Okay. Think about how we utilize this. And if you think this is really hard and you're not really sure how to do, you can still go back, use the convolution table in combination with property number 5 that has something to do with the shift. And of course, since you have multiple terms, to distribute a term properly, you need to use property number 3 as well. So mathematically, if you go to the math, you'll be able to find the result. Another approach is to utilize the property that the system is linear and time invariant and reuse what we have derived above. Okay. So this is the end of this second lecture video.